Okay, folks, so flux through metabolic pathways is often linked to energy availability and need. So we need to understand the molecules that we're talking about when we're talking about energy in the cell. And I'm sure some of these are not new to you, right? The high energy molecules we will discuss in this class are ATP, right? Molecules containing phosphoanhydride bonds or phosphorylated compounds, and bioester-containing compounds such as CoA. These first two types of molecules contain high energy bonds, and we'll talk about why that is shortly. The last type of molecule, reduced coenzymes such as NADH, NADPH, and FADH2, are considered high energy because the movement of electrons from those molecules to other molecules involves the release of energy. And we will understand this to a greater extent when we talk about electron transport and oxidative phosphorylation. So more to come there. Let's start with phosphorylated compounds. So what we'll talk about now is relevant to ATP and other phosphoanhydride containing compounds. These compounds release a lot of energy upon cleavage of the phosphoanhydride bond. Molecules like ATP contain two high energy bonds, two phosphoanhydride bonds. So this bond here is phosphoanhydride, as is the second one. The last bond between the adenosine and the first phosphate, or the alpha phosphate, is a phosphoester bond. It is not high energy. ATP is hydrolyzed either at the gamma phosphate or at the beta phosphate, right? So ATP is converted either to ADP or AMP. We consider ATP to be a high energy signal because it contains the high energy bonds. Both AMP and ADP we consider low energy molecules because, excuse me, that is worse handwriting than normal. They lack hydrolyzable bonds, right? When ATP is hydrolyzed, it is converted either to ADP or AMP, so those are low energy signals. Now, why are these bonds high energy? Let's talk our way through them. There are three reasons why the bonds release so much energy. First, resonance increases upon hydrolysis, and we'll talk through this. Second, repulsion between adjacent phosphate groups is reduced. And third, there is a larger solvation energy for the hydrolysis products. Reason number one. There is increased resonance upon hydrolysis. So I am going to abbreviate the adenosine part of ATP just as A here to simplify the drawing. But then I will draw out all the phosphates. And when we hydrolyze it, we're going to hydrolyze it to a DP and a phosphate, although the same is true for AMP. let's see how much resonance there is before and after hydrolysis. And I'm not going to just draw each separate resonance arrow out. I'm just going to draw them all out and hope that you please forgive me. So this oxygen could resonate, this oxygen could resonate, as could this one, and then of course we could push lone pairs up onto any of those carbonyls, excuse me. Additionally, let's draw those arrows for a DP and the phosphate. And then let's count them up. On the left-hand side, I see 1, 2, 3, 4, 5, 6, 7 resonance arrows. On the right, 1, 2, 3, 4, 5, 6, 7, 8. So on the right-hand side, folks, we have increased the amount of resonance that can be performed. And if you learned anything in organic chemistry, fingers crossed, you learned that resonance increases stability. So if the products are more stable, we must have released energy. That is reason number 1. Reason number 2, reducing repulsion between phosphates. Again, let's simplify the molecules, but I'm going to further simplify by just drawing out the phosphates and including the charge. Oops. Yeah. Let's try that again. Okay. On the left-hand side, you see that right next to each other, we have 3 total negatively charged functional groups. Let's compare that on the right. On the right-hand side, we only have 2 negatively charged functional groups covalently linked to each other. So when we hydrolyze a phosphate off, we have decreased the repulsion through Coulomb's law experienced by similarly charged things repelling. Finally, 3, increased solvation energy upon hydrolysis. And I'm going to further simplify this drawing. In the beginning, we have ATP. This molecule is a single ion. It has a charge of -4. We then convert it into ADP and phosphate. And then phosphate is technically abbreviated as PI like that. And so you can see we've gone from a situation where we have a single ion to a situation where we have 2 ions. Thinking back to the first day of class, we understand that each of these ions could be solvated or surrounded by hydration shells. That is a favorable interaction because we have the interaction of an ion with something polar. We have those strong ion-dipole interactions. So, since we can perform more of those interactions when we have 2 ions, again, the products are more stable. Another reason why we release so much energy. Now, as a side note, when we are releasing energy within the cell, hydrolysis of these bonds, release of this energy is going to be coupled to a process that requires the energy input. Think conservation of energy. The cell doesn't just want to waste the energy released from hydrolysis of ATP. It will take that energy released and use it for something, and we will see that this semester. I want to mention before we move on to the next type of high energy molecule that there are various molecules with different amounts of energy release for each molecule. For example, there are some higher energy molecules that maybe have more resonance and charge separation upon hydrolysis. They will release more energy. Excuse me. And we can compare those to lower high energy compounds that really release much less energy. Here's another table, right? Molecules on the top can release sufficient energy to synthesize a molecule that requires less energy. Up next, we'll talk about the next high energy molecule, thioesters.